Welcome to the Deep Dive, the show where we unpack the most impactful research, pulling out those aha moments that genuinely expand your understanding. Today, we're plunging right into the core of what powers our digital world. Electronics. Think about the relentless pace of innovation. AI, the Internet of Things, self-driving cars, VR, they all demand more and more computational power.
On faster speeds, better energy efficiency.
Exactly. It's just this constant demand.
Right. And the challenge is the silicon-based transistors that have basically been the workhorses of our digital age, they're rapidly nearing their fundamental physical limits, especially as we try to shrink them down, sub-10 nanometer scales. We're really hitting a wall.
So it restricts further improvements, like in chip performance.
Performance, power efficiency, how densely we can pack components onto a chip, all of it.
Right. It's like trying to get a race car to go infinitely faster by just making the engine blocks smaller and smaller. Eventually, the physics just say no.
Pretty much. So the big question is, what's the path forward when our tried and true material is kind of tapped out?
And that's what this deep dive is all about, a potential game changer. Two-dimensional or 2D atomically thin semiconductors.
Yeah, these are materials so incredibly thin, they're literally just like a few atoms thick. We've seen promising candidates, molybdenum disulfide, tungsten diselenide.
Right.
But the material we're focusing on today is indium selenide, or InSe.
InSe, okay.
And what's fascinating here is its theoretical promise. It looks really good on paper.
Okay, this is where it gets really interesting for me because, yeah, theoretically, InSe looks like a superhero material. Its electrons apparently have a super low effective mass, like 0.14 millu compared to silicon's 0.19 millisieverts.
Exactly. And that lower mass means they can accelerate incredibly fast. Quicker response times.
Faster switching.
Faster switching. And its thermal velocity, essentially how fast electrons move through the material when it's heated, is higher than silicon's too. Over 1.3 centimeters compared to 1.2 centimeters for silicon.
Okay, so higher velocity means faster switching again, and maybe less heat.
Less heat generated, yeah.
Yeah.
Which is crucial for power efficiency. And then there's its theoretical mobility.
Ah, mobility. That's basically how easily electrons can zip through the material without getting scattered around, right?
Precisely. And for InSe, it clocks in theoretically at a staggering 1,000 square centimeters per volt second at room temperature.
Wow, 1,000. That's incredibly high. It suggests a very, very smooth ride for electrons.
It does. And crucially, for any semiconductor, it has an appropriate band gap, over 1.26 electron volts compared to silicon's 1.14 EV.
And that band gap is key for switching, right? Turning the transistor on and off cleanly.
Absolutely. It dictates how efficiently you can switch between those on and off states.
Yeah.
So yeah, all these properties give InSe a significant theoretical edge.
Okay, but theory is one thing. You mentioned these impressive numbers were mostly for tiny individual flakes of InSe, like peeled off layers.
That's right. Created by literally exfoliating them, like you might peel layers off with tape. And while these microscale flakes showed exceptional performance, the scalability for integrated electronics, the kind that powers your smartphone, or a data center that ultimately relies on large-scale, high-quality InSe wafers.
Right. A tiny perfect flake is great, but you need a whole dinner plate of the stuff, perfectly uniform.
Exactly. So it raises the really important question. How do you go from that perfect microscopic flake to a uniform several-inch wide wafer?
That's the practical hurdle, isn't it? Every great material needs a great manufacturing process to actually use it.
And current wafer-scale production methods, things like MOCVD or molecular beam epitaxy, they've consistently produced InSe films that just underperform.
Underperform compared to other 2D materials, or even compared to InSe's own potential.
Both, actually. Certainly compared to what InSe should be capable of based on those flake studies.
Okay, so what were the roadblocks? Why was it so hard to make good InSe wafers?
Well, there have been two main roadblocks. The first is something called phase diversity.
Phase diversity.
Yeah, the indium-selenium system is surprisingly complex. There are at least 4 stable phases, different ways the atoms can arrange themselves. InSe, IntelAC3, In4SL3, In6SE7.
Okay.
And just a tiny wiggle in the composition, a slight deviation from that ideal 1-to-1 atomic ratio for InSe, and you can trigger unwanted phase transitions. You end up with bits of these other materials mixed in.
So it's like trying to bake a very specific, delicate cake, But if your flour to sugar ratio is off by even a fraction, it spontaneously turns into like bread or a cookie instead.
That's a perfect analogy.
Hmm.
And these unwanted phases lead to huge swings in device performance. They can even degrade the material over time.
Not what you want in a reliable chip. Okay, so phase diversity is problem number one. What's number two?
Problem number two is just plain poor crystallinity. It's incredibly difficult to maintain that precise stoichiometric balance, that 1-to-1 ratio between indium and selenium during the growth process.
Why is that so hard?
The main culprit, vapor pressure. Selenium's vapor pressure is approximately 7 orders of magnitude greater than indium's at typical growth temperatures, around 500 degrees Celsius.
Whoa, 7 orders of magnitude. That's a million times. 10 million times.
10 million times, yeah.
Huh.
It's a massive difference.
So it's like trying to keep water and, I don't know, molasses mixed perfectly, but the water just wants to evaporate incredibly quickly, leaving you with too much molasses.
Exactly. The selenium just tends to evaporate much, much faster than the indium. It makes it incredibly hard to maintain that critical 1.1 ratio you need for pure, high-quality InSe.
And without that purity and high crystallinity, you just can't unlock InSe's full potential.
Correct. And until this new work, that's been a really significant barrier.
Okay, so clearly a radically new approach was needed, which brings us to the breakthrough.
It does. That brings us to what these researchers developed. A strategy they're calling the solid-liquid-solid, or SLS strategy.
Liquid-solid SLS. Okay, unpack that for us. How does it tackle those two big problems?
All right. So first, to solve that phase diversity problem and maintain this strict 1.1 ratio, they came up with a really ingenious solution.
Okay.
They started with an amorphous InSe wafer, basically, InSe material, where the atoms aren't arranged in a nice crystal yet. Then they sealed this wafer with liquid indium.
Liquid indium, but indium's a metal, isn't it solid?
It is at room temperature, but it has a very low melting point, only about 157 degrees Celsius. So they heat it just enough to melt it and use it to completely seal the amorphous InSe wafer.
Ah, okay, so it creates like a sealed chamber around the wafer.
Precisely. A completely sealed space. This prevents any atomic loss.
Hmm.
No selenium escaping during the high temperature growth step, which happens later at around 550 degrees Celsius.
Clever. So the ratio stays locked in at 1.1. Problem 1 solved. What about the crystallinity? Problem 2.
That's where the solid-liquid-solid part comes in. It describes the novel growth mechanism they discovered. Recrystallization of that amorphous InSe happened right at this interface with the indium-rich liquid.
So the liquid indium isn't just a seal, it's actively involved in the crystallization.
Exactly. They even introduced trace amounts of additional indium atoms from the surrounding liquid indium and the saturated indium vapor within that sealed space. These extra atoms and the liquid phase itself are key.
How does that work? What's the physics?
Well, first, density functional theory calculations. These are powerful computer simulations, show that amorphous InSe has a higher formation energy than crystalline InSe, about 0.38 electron volts per atom higher.
Meaning it wants to become crystalline, like a ball rolling downhill, energetically speaking.
Exactly like that. The crystalline form is the lower energy, more stable state, but getting there can be slow. The liquid indium-rich interface acts like a catalyst. It kinetically promotes this transformation.
Oh.
It provides this medium where the indium and selenium atoms from the amorphous layer can easily dissolve, move around quickly, and then reprecipitate or rearrange themselves into that perfect crystalline InSe structure.
So the liquid helps the atoms find their perfect spots much faster than they could in a solid.
That's the idea. And they actually saw evidence of this. Using techniques like cross-sectional scanning transmission, electron microscopy, STEM.
Which lets you see atoms, right?
Yeah, you can see the atomic columns.
Yeah.
And corresponding FFT patterns, which analyze the structure, actually showed the presence of this thin, indium-rich, liquid-like interface right where the crystallization was happening.
Wow. Being able to actually see the mechanism at work. That's powerful validation.
Absolutely.
In the results, did it work on a larger scale?
It did. The strategy successfully produced high-quality InSe wafers approximately 5 centimeters in diameter on sapphire substrates.
5 centimeters, that's getting into practical territory for chip manufacturing.
It is, and not just large-scale, but exceptionally uniform.
Yeah.
They took optical images from 12 different spots across one of these 5-centimeter wafers.
Yeah.
Uniform contrast everywhere. Looked the same all over.
Yeah.
Then they did Raman spectroscopy on those areas.
Which tells you about the material's structure and quality.
Right. And the spectra were nearly identical across the wafer, really proving large area uniformity. And get this. The surface roughness dropped dramatically.
How dramatic.
Well, the starting amorphous material was rough on an atomic scale, around 415 picometers. The final crystalline wafer only about 37 picometers rough.
Whoa, that's incredibly smooth, almost atomically flat. That must be critical for building tiny devices on top.
Absolutely critical.
Yeah.
And the crystallinity itself was also outstanding.
How did they check that?
Several ways. One cool technique was hydrogen etching. When they exposed the wafer to hydrogen, it etched away tiny triangular holes. And crucially, all these triangles had the exact same orientation across a large area.
Which tells you.
It's strong evidence of a single crystal structure, like one massive, flawless diamond lattice instead of a bunch of smaller crystals stuck together randomly.
That's a great visual. A single giant crystal.
They also used optical techniques like second harmonic generation, SHG. The patterns they got were consistent everywhere, again pointing to that monocrystalline nature. And low X-ray diffraction, LXC, which gives a bigger picture view, showed sharp, consistently arranged spots across a whole square centimeter region, confirming high crystallinity on a large scale.
So uniform, smooth, single crystal. It sounds like they really nailed the material quality. Did they look even closer, like at the atomic arrangement?
They did. Using electron diffraction and those high-resolution HADF STEM images, they confirmed the high crystallinity of the InSe lattice right down to the atomic level. They could measure the precise spacing between atoms and even determine the stacking order and ideal ABC stacking, which is kind of the gold standard for this type of crystal quality.
Okay, this is impressive material science, but the real payoff is in the electronics, right? How did these wafers perform when they actually built transistors on them?
Right, that's the ultimate test. They fabricated large-scale integrated arrays of field effect transistors, FTs, directly on these InSe wafers.
And getting good electrical contact can be tricky with new materials.
It often is. They used a clever trick here, doping the metal contacts with a bit of yttrium. This helped achieve what's called robust ohmic contact, meaning electrons could flow smoothly into and out of the transistor, and it avoided something called the Fermi-level pinning effect, which can hinder performance.
Smart. Okay, so how did the transistors do? Let's start with maybe larger ones, say 480 nanometer gate length.
Yeah, for those 480 nanometer devices, the performance was truly outstanding. The average field effect mobility was 287 centimeter VU and VS.
Which is good.
Very good.
Yeah.
The peak value they saw was even 347 centimeter for VS. For context, this is higher than all other reported 2D devices made from grown films, not just flakes. And importantly, it meets the target set by the International Roadmap for Devices and Systems, the IRDS benchmarks.
Okay, so it meets future industry requirements. What else?
They also achieved a near Boltzmann limit subthreshold swing, or SS, averaging as low as 67 millivolts per decade.
And a low SS means?
It means the transistor switches from off to on very sharply, very efficiently. It's close to the theoretical minimum energy needed to flip that switch.
Yeah.
Basically, it's about as energy efficient a switch as physics allows.
Wow. Efficient switching is key.
Definitely. And they also got a high saturation current density, 892 microamps per micrometer. That means the transistor can deliver a lot of current when it's on, which translates to speed, significantly higher than other similar 2D devices.
Okay, that's impressive for the larger devices. But the real push is towards smaller, right? Did they test really tiny transistors?
They did. They went down to ultra-short 10 nanometer channel devices.
10 nanometers, that's tiny. How did they perform?
Amazingly well. They showed nearly ideal switching behavior. The SS was still very low, around 79 milliV per decade, and the on-off ratio, the difference between on current and off current, exceeded 10 million to 1.
10 million?
Yeah, which meets the really stringent requirements for advanced logic circuits, like in the processors we rely on. And get this. They operated at an ultra-low voltage of just 0.5 volts.
Half a volt. That's incredibly low power.
Extremely low power. And even at that voltage, the off-state current, how much it leaks when it's supposed to be off, also meant the IRDS requirements for both high-performance and high-density applications. Low leakage is crucial.
So high performance, super low power.
Exactly. Their plots comparing on-off ratio versus current showed performance at least 2 orders of magnitude, 100 times better than other competing 2D materials.
100 times better.
And the current drive was excellent too. Saturation current density up to 1.2 milliamps per micrometer at 0.8 volts. And they hit that magic 1 milliamp per micrometer mark at an ultra-low drain voltage of just 0.46 volts.
Okay, these numbers sound fantastic, but how do they stack up against, say, the absolute cutting edge of silicon technology, like Intel's latest stuff?
Great question. The researchers did exactly that comparison. They benchmarked these InSe devices against Intel's 3-nanometer technology nodes and other top 2D transistors.
Across key metrics.
Across 6 key parameters: operating voltage, gate length, DIBL, that's drain-induced barrier lowering. Basically how well the off-state hold up as you shrink.
Okay.
Effective mass, on-off ratio, and ballistic ratio, how efficiently electrons shoot through without scattering.
And the result?
The InSe devices showed superior comprehensive electrical characteristics across the board.
Better than state-of-the-art silicon.
In these key combined metrics, yes.
Yeah.
And here's the really mind-blowing part. They looked at speed and efficiency metrics. The intrinsic gate delay, how fast the transistor can switch, was as low as 0.39 picoseconds.
Pico. That's a trillionth of a second.
Trillionth of a second. Insanely fast. And the energy delay product, EDP, which balances speed and power use lower, is better reached an exceptionally low value of 5.27 times 10 to the minus 29 joule seconds per micrometer.
Okay. Numbers are getting small. What does that mean in context?
It means these values exceed the predicted limits for silicon-based technologies outlined in that IRDS roadmap, not just for today, but projecting all the way out to 2037.
Wait, hang on. This material is already demonstrating performance metrics that silicon isn't expected to reach for over a decade.
That's what the data suggests. It's performing beyond the future predicted limits for silicon in some key areas.
So this material is literally kind of future-proofed against silicon's limits for the next decade and beyond. That's not just an incremental step.
It really isn't. It feels like it could be a fundamental shift.
It's like finding a new building block that just changes the timeline of what we thought was possible, pushing things years, maybe decades ahead.
That's a good way to put it. This solid liquid-solid strategy really seems to provide a scalable way to get these high-quality InSe films with amazing uniformity and crystallinity.
Which then enables these transistor arrays with truly outstanding performance, high mobility, near-perfect switching.
Even for large-scale devices.
Yeah.
And then you have those ultra-short 10-nanometer transistors outperforming current state-of-the-art silicon benchmarks.
So stepping back, what's the broader significance here for you, the listener, and the tech that shapes our daily lives?
Well, it strongly suggests that 2D InSe, made using this method, could become a critical material. It could potentially replace or at least augment silicon, especially at these incredibly small scales where silicon is struggling.
So new possibilities for device performance.
Exactly. It paves the way for vastly more powerful, more energy efficient, and more integrated electronic devices. Just think what that could mean for the future of AI, the Internet of Things, next generation computing. It touches everything.
Okay, let's try and distill this down. If you were to take away just a couple of key messages from this deep dive into indium selenide, what would they be?
Okay. First key takeaway. We have a powerful new manufacturing tool. This solid liquid-solid SLS growth strategy effectively solves those long-standing problems of getting pure phase and highly crystalline InSe films on a large scale.
Right, by controlling the ratio and using that clever liquid interface.
Exactly. That's takeaway number one, overcoming the fabrication hurdles.
Okay, takeaway number two.
The performance is genuinely redefining limits. Transistors built on these wafers show unprecedented electronic performance for 2D films. They're not just beating other 2D materials, they're actually exceeding those future predicted limits for silicon in critical areas like speed and energy efficiency.
Performance that redefines the limits. Got it.
Is there a third? I think the third is about the foundation for the future. This isn't just a small tweak. It looks like a potential new foundation for future electronics.
How so?
It positions 2D indium selenide as a really strong contender to take over where silicon is hitting its limits. It could lay the groundwork for the next wave of powerful, low-energy devices needed for advanced AI, IoT, high-performance computing, all that future tech.
A new foundation for future electronics. Okay, those are three really solid takeaways.
So as you, the listener, reflect on this, maybe consider the profound impact these kinds of material science breakthroughs happening right down at the atomic scale can have on the devices that really shape our everyday lives.
Yeah, from the phones in our pockets to the massive data centers powering AI, it all comes down to these fundamental building blocks.
It really does.
And this work definitely leaves us with a provocative thought, doesn't it? How might this ability to create electronics that operate beyond silicon's theoretical limits fundamentally change what's possible?
Yeah, think about fields like neuromorphic computing, trying to build chips that work like the human brain, or truly ubiquitous sensing, tiny sensors everywhere running on almost no power. What does this unlock?
And maybe the most exciting question of all, how soon could these future technologies enabled by materials like InSe actually become a tangible reality, in our world, maybe in your hand or woven into the fabric of your home?
That's the billion-dollar question, isn't it? But this research certainly makes that future feel a lot closer.